Imagine Sahara. Annual average temperatures over 29 degrees Celsius. Only 50 years from now, if we don't cut our emissions of greenhouse gases substantially, 1/3 of the world population could be living in areas with Sahara-like temperatures, covering 1/5 of the Earth's land surface. This is a future no one wants. The world's nations agreed in Paris 2015 to act decisively and limit global warming to well below 2 degrees Celsius compared to pre-industrial levels. We can all contribute to the sustainability transformation needed, but this work needs to be based on the best available science so that we know what we're doing and so that we act on what truly matters. In this talk, I will condense decades of research and present the latest findings to equip you with the knowledge that everyone should have about climate change. First of all, climate change is already affecting both people and nature. It's difficult for science to attribute a specific weather event to climate change, but we can conclude that the intensity and number of extreme weather events are increasing as a result of global warming. And here are some examples from the United in Science report of 2020. Hurricane Harvey, one of the most devastating hurricanes on record, caused more than $125 billion in losses when it hit the Houston area in the US 2017. Human influence increased the amount of rainfall associated with this hurricane by about 15%. During the East Africa drought of 2016-2017, 6.7 million people in Somalia were food insecure. This drought was strongly influenced by warm sea surface temperatures in the Western Indian Ocean, amplified by global warming. Of course, drought and heat waves substantially increased the risk of wildfires. The 3 largest economic losses on record from wildfires all occurred in the years 2016 to 2020. The abnormal heat in January to June 2020 was at least 600 times more likely as a result of human-induced climate change. This led to unprecedented wildfires in the Arctic region. And in eastern Australia, more than 10 million hectares were burnt. The likelihood of the weather conditions that led to those wildfires has increased by at least 30% since 1900. We're also losing species and ecosystems at alarming rates, undermining the life support systems that we all depend upon. And all of this is happening already at a global warming of 1 degree Celsius compared to pre-industrial times. Now, 1 degree might not sound so much, but this is a global annual average which is not evenly spread across the planet. The warming is faster over land and by the poles, so the Arctic is already 4 degrees warmer. Let's look at the change in temperature since the last ice age. We are here, and this is where we're heading if countries do everything they've promised so far to do to curb emissions. Fulfilling every promise would lead to 3 to 4 degrees average warming by the end of this century. And that's a temperature that the Earth hasn't experienced in 3 million years. What would that mean? Well, a sea level rise of at least 60 centimeters, maybe even 1.3 meters, flooding coastal cities and islands, and threatening salt intrusion in groundwater. Ecosystems like coral reefs will collapse, and new diseases are expected to emerge. Drought, heat waves, and melting glaciers would affect access to water and food, increase fires, and make many places inhabitable to people. We don't know how people would respond to such a world, but conflicts and large migrations are not unlikely. To get a feeling for the magnitude of a 3-degree change, note that 3 degrees colder means ice age. In this picture, I would also like you to notice the stability of the Holocene, this period in which our civilizations have developed. This is the kind of climate that we know that we can thrive in. And now we're putting it at risk. But hasn't the climate always changed? Let's go back further in history and have a look. A key driver behind this warming was discovered already in the 1800s, carbon dioxide concentrations in the atmosphere. They cause a greenhouse effect, which is amplified by our emissions. In this chart, we see global average concentrations of carbon dioxide in the atmosphere over the past 800,000 years. And we will start to go to the Industrial Revolution of 1850. The periodic fluctuations in carbon dioxide concentrations that you see here coincide with the onset of ice ages and interglacials. These fluctuations are caused by changes in the Earth's orbit around the Sun and the tilt of the Earth axis, called Milankovitch cycles. Over this long period, all up until the year 1850, the onset of the Industrial Revolution, atmospheric concentrations of carbon dioxide did never exceed 300 parts per million. Now, with the onset of the Industrial Revolution and the rise of human emissions of carbon dioxide, we see a rapid increase of carbon dioxide in the atmosphere. For the first time in 800,000 years, concentrations did not only rise about 300 parts per million, but are now above 400 parts per million. And in a business as usual scenario, we're heading for concentration levels between 750 and more than 1,300 parts per million. It's not only the level of carbon dioxide in the atmosphere that matters, but also the rate of change. Historical changes occurred over centuries or even thousands of years, but it took us only a few decades. In fact, half of the emissions occurred after 1990. So this gives species, planetary systems, ecosystems, and us much less time to adapt. So, where do emissions come from? This is the concentration of carbon dioxide in the atmosphere, 1850. Our burning of fossil fuels and production of cement have added an equivalent of 207 parts per million. Our land use, so that's industrial agriculture and forestry, have added another 96. But interestingly, not all of these emissions have ended up in the atmosphere, only half. And the rest have been absorbed by our oceans and vegetation on land. And then there's always, of course, some parts that you can't explain exactly with our current analysis and methods. But our living planet has acted as a buffer, maintaining the stability of the Holocene climate. Thank you, biosphere. But we now see signals that this capacity is threatened. I will never forget the moment when a colleague of mine came into the office with the results of his research group's latest analysis. His face was grey as he showed them to us, asking, how do we share these numbers with the world without causing panic? What they had found was indicating that so-called tipping elements could be triggered by global warming and further accelerated out of our hands. These results were eventually published. I will talk you through them. And what I will show you now is new research from the frontiers. Follow-up studies might come to nuance this picture, but because of the severity of the consequences, we need to take these mechanisms into account. Earth system scientists have so far found 15 elements on the planet that help regulate the climate, either by cooling it, like the ice on the North and South poles, or by absorbing the greenhouse gases, like the forests. But now, 9 of these show signs of weakening. And if they're pushed too hard, they can tip from stabilizing the climate to accelerating the warming. Let's start in the Arctic. Here, ice is white, reflects heat, but when it melts, it becomes darker, absorbing more heat. The increased melting affects the salinity in the waters, hence affecting the Atlantic circulation, which in turn affects global rainfall patterns, taking us all the way down to the Amazon. Forests like the Amazon absorb carbon dioxide, but when they dry up, they can catch fire and release that stored carbon into the atmosphere, causing even more warming. In the Amazon, this development is accelerated by producers of soy and beef who clear the forest for farming. Another group of colleagues of mine traced the money behind these activities and found a handful of large institutional investors to be involved. And in a way, they hold the key to our future in their hands through their choice to fund these activities or not. Because at a certain tipping point, the Amazon loses its capacity to create its own rain and slowly but surely turns into a savanna, releasing carbon into the atmosphere instead of absorbing it. Recent studies show that 40% of the Amazon is now in a state where it could become a savanna. The boreal forests and peatlands here in the north are equally important. The 2020 fires in the Arctic region released 244 megatons of carbon dioxide. And when the permafrost melts, it releases methane, which is another powerful greenhouse gas, accelerating the warming. So these elements are approaching tipping points. They might trigger each other. We're probably not there yet, but this is a risk that we face unless we bend the curve of emissions and stop the erosion of critical ecosystems very soon. So what can we do about this? First of all, I'd like to emphasize that stopping human development is not an option. As we all know, in spite of the fantastic progress, many people still don't have access to basic resources. 1 out of 10 in the world live in extreme poverty. 1 out of 10 experience severe food insecurity. 1 out of 10 lack electricity, and 1 out of 4 lack basic sanitation. And almost half of the world population are still not connected to the internet. When the COVID-19 pandemic hit in early 2020, causing planes to stay on the ground and factories to stop and people to stay at home, some people saw this as a chance for the climate to recover. But the daily emissions only dropped by 17% back to the emission levels of 2006, with close to no effects on the rate of global warming. As we speak, emissions are on the rise again. So what we need to do instead is to shift our economy so that it meets the needs of all within the capacity of the planet. We need renewable energy, sustainable food systems, fossil-free transports, and green buildings. We need circular industries, and we need to restore our ecosystems. And we need to move fast. As a rule of thumb, the world needs to halve emissions every decade, and richer countries need to go faster. This is the roadmap to rapid decarbonization. Because if we are to stay at the 1.5-degree threshold, as agreed in Paris, and minimize the risk of accelerating warming through these tipping elements that I described, the atmosphere can absorb no more than 420 gigatons of carbon dioxide, as concluded by the IPCC back in 2018. Since around 42 gigatons are emitted globally every year, this budget would be used up in less than 10 years from then. So instead of waiting years and years to act and then drop straight to zero, Professor Johan Rockström with colleagues suggests that we follow a carbon law path, halving emissions every decade. This idea was inspired by Moore's law, observing that computer capacity doubles every 2 years. So in comparison, the carbon law is actually pretty slow. At the same time, we need to turn agriculture from a source into a sink. We need to maintain the natural carbon sinks, and we need to develop new ones. To date, no artificial carbon sinks are able to remove carbon from the atmosphere at the scale needed to fight global warming, which is why we need to maintain the Earth's capacity of carbon sequestration. Luckily, it's technically and biophysically possible to follow the carbon law. The Exponential Roadmap report investigates existing scalable solutions to achieve the first halving. In sector after sector, it is within reach. And in the meantime, we can develop the solutions needed for the next halving. Let's look at energy first, responsible for 18.5 billion tons of emissions annually. There is no room in the budget for investments in new carbon dioxide emitting energy systems, but wind and solar are on an exponential trajectory and are now cheaper than fossil fuels in many places, enabling the first halving together with more efficient use of energy. Industry. Here, the first halving could be achieved by shifting to more efficient material use, recirculation, and better management of refrigerants. Let's look at the potential of nature-based sinks. With reforestation, biochar, and improved agricultural practices, nature could help us store up to 9 billion tons of carbon dioxide annually. Finally, food. Shifting to plant-based diets and reducing food waste would ensure that a growing world population get the food they need while emissions decrease. And this shift can in many cases generate economic growth and create jobs. The global economic benefit of a low-carbon future is estimated at $26 trillion by 2030, compared with staying on the current high-carbon pathway. And let's look at Sweden, an interesting example. Here, GDP per capita has increased by about 50% since 1990. At the same time, emissions from production in the country have decreased almost 40%. And even emissions from consumption have fallen by 20%. However, it's all about the content of that economic growth. See here, in 2009, how both the economy and the emissions fell due to the financial crisis, only to just bounce back as soon as the economy recovered. So it's particularly important after a crisis to really build back better and invest in a better future for all. To conclude, humans are changing the climate through burning of fossil fuels and land use. The preconditions of our civilization are at risk. We're approaching tipping points. Basic human needs are not yet met, so stopping human development is not an option. But all of humanity can thrive within the capacity of the planet, and this shift is technically and biophysically possible. Important steps are being taken, but we need to accelerate the transformation. Because the decisions we take now will influence the generations to come. It's up to us to create the future we want, and we are all needed in this journey. Our generation can make or break the sustainability transformation. Thank you.